Okay, welcome everyone to another 10-minute lecture. Just a reminder for everybody here in the room, we have microphones all the way at the top, if you see them in the ceiling, so you can communicate with the speaker that's on Zoom today. You don't have to get up and listen to everything. It's everywhere in the room. Today we have Andrew Dawson. Professor Dawson was faculty at the University of Nottingham for almost 37 years. His research specializes in mechanical, hydraulic, and environmental characteristics of pavements and their constituent materials, especially their characteristics and performance of unbound granular materials. He was chair of the TRB Aggregate Committee in 2016 to 2022. And he holds a bachelor's degree in engineering from the University of Lancaster and a master's degree in soils mechanics from the Imperial College of London. So please welcome Professor Dawson.
Thank you very much. It's a pleasure to be with you, if only electronically. If I go to sleep in the middle of my talk, it's because where I am, it's late in the evening. So, but I'll try and keep awake. And more importantly, I'll try and keep you awake too. So I've given you this title, The Fourth Power Law Fiction. Now, let me ask you, do you believe in UFOs?
Yes.
Yes.
Yeah. Oh, you can't hear us.
Yeah.
Right.
Okay, so a similar question. Do you believe in the fourth power law?
What is that?
What is that?
In our presentation today, I want to sort of what is the fourth power law? Think a little about where it came from, the Azure road test, and then seek to show you that there are lots of examples and which don't fit, and lots of assumptions we make in using it which aren't really sustainable. And then I'll try and make a little bit of discussion and draw some conclusions at the end. So what is the fourth power law? Well, you may have seen it in this way, which says that the number of axles of one particular load type can be equivalent to a number of axles of a different load type according to the relationship shown here, however you prefer to write it. And they then say that F, the power is 4, maybe. Now, that has the appearance of a fatigue relationship. Those of you who know about material fatigue, it's very similar to a fatigue relationship, though it's in terms of load and not strain. Usually when we talk about fatigue, we talk about it in terms of strain. So if I was to take the logarithms of the equation on the left at the top, I'll get the one at the bottom there. And I can plot that graphically in this way. So you've got the logarithms of number of cycles along the bottom and the logarithm of load vertically, and you get a gradient of minus the power F. So it does have looks a bit like a fatigue relationship. Why do we need this so-called law? Well, axle loads vary across our pavement. They're not all the same. They vary in magnitude. Cars less than half a ton, trucks more than 12. I'm talking about axle loads here. Number of vehicles, well, maybe less than 250 on a low volume road, maybe 50,000 or more on a freeway lane. And they vary in spectrum. There's cars, there's trucks, and the trucks have different axle loads as well. And for those of you who won the War of Independence against the UK, but failed to win the War of Independence of metric units. Those I'm going to use metric units, but if you're more familiar with US units, then a ton is about 2.2 kips. Now, the pavement engineer, he knows increments of pavement damage are somehow proportional to axle load, but only somehow. He or she doesn't know the variation in axle loads precisely, and you can't design for each axle that the road is going to take, even if you did know all the axles that it was going to receive. So we somehow need a simplifying axle load to which the damage can be related. So that's why we need it. So this above relationship, the fourth power law, allows equivalencing actual loading. So let's call this P2, that's an actual load, an actual load, and there are N2 passages of it, to some reference loading, which we'll call P1, and there are N1 passes of that reference load. And similarly, we can do that for other actual loads, P3, P4, however many you like, and we can equivalence those all back to the standard actual load, the reference one, P1, and we can add up all the numbers that we've got. And so we can get the total number of reference loadings, and we can use that in design. But why use this relationship, this power law relationship? Surely there are others we could use to make this equivalencing. Why do we want to use that one? And why does F have to equal 4? Why shouldn't it be something else? Well, to answer those questions, we need to go back to the Azure road test. Now, the Azure road test was performed in the late 50s, early 60s, near you, much nearer you than me. And on a particular subgrade, the traffic all went at a constant 56 kilometers an hour. What's that? That must be 35 miles an hour? Not sure. The traffic was canalized, that's to say every vehicle went behind every other vehicle. And there are a bit over 1 million axle loads over a 2-year period or thereabouts. And on any one particular road or any one particular track, there was only one axle load. So there was never a mix of axle loads on the same pavement. There were different pavements with different axle loads. And most of the failure occurred in the subbase and primarily during the spring thaw. But the failure criteria was serviceability. In those days, there weren't all the sophisticated equipment we have these days. And so they sat people in a car and drove those people around, and those people assessed the quality of the road through the vibrations they felt in their buttocks. So it's not a very scientific way, you might say, but that's how it was done because that's all they could do in those days. And they summarized the results. Well, some of the results were summarized in the 4th power law, as we've seen that as already. Now, what this says is that let's actually look at what this law actually says. It says that the decay due to M1 passes of load P1 are the same as the decay of N2 passes of load P2 at this limit serviceability condition, when the people in the car felt the road was at the same limiting trafficable condition. Then they looked at the number of passes in one pavement and the number of passes in another with the 2 different loads on, and equivalence those pavements. But important to know what they were doing and what they weren't doing. So it doesn't say, even though we might like it to say, that cracking or rutting or any other failure method equals decay, because we don't know how those contributed to the serviceability assessment these people did sitting in the back of a car. It doesn't say that decay is proportional to load to the power 4 or any other power come to that, because they only looked at a condition where the decays matched, where the roughness matched. So it doesn't say that decay is proportional to N either, the number of passes. If they'd only done half the number of passes, would they have felt just as uncomfortable or only half as uncomfortable, or we don't know. And then it doesn't say that if you had one type of traffic followed by another on the same pavement, that would be the same as the order reversed. So it doesn't mean that A passes of load A followed by N passes of load B is equal to the same thing the other way around. Lots of things it doesn't say. And they produced this chart here, and as you see, it's there was somewhat fudging to get this. And as you see, actually, they didn't get power of 4, they got a power of 4.15. But there you are. Now, added to this has come the miners law. I don't really know I know what miners law is, but I don't really know how it got added to this data. The minor, or strictly speaking, the minor Palmgren law says that you can add up the damage caused by one set of cycles to the damage caused by another set of cycles. So if we've got, what it says here is that if you've got I numbers of cycles of load I, compare that to the number of cycles you need to apply at that size of load in order to get a unit of distress, whatever distress is, complete distress. So if you've got Ni is less than the number of failure, then we've got a proportion of the decay, and then you can add that to decay caused by other cycles, other loads. So this says that the order of loading is unimportant. We don't know that, but that's what this relationship says. It says that damage by twice the number of cycles of any particular load gives you twice the damage. But it doesn't say that linearity or a parallel relationship with load is necessary. But it does say that linearity with N is necessary. So I think you can see already that there's quite a few differences. If you're familiar with the fourth power law as how it's used, I think you can see there's quite a few differences between how we use it and what the original information said. And of course, damage greater than the limit is meaningless in the minor Palm-Graham relationship. You can only get the complete disturbance, complete decay. I might also take issue with the word law. I mean, a law suggests ultimate truth, like laws of gravity or Newton's laws of motion. But the fourth power law is empirically derived and or empirically validated. And as I'm going to show you, there are many counterexamples and invalid assumptions as well. So putting it, sort of squashing it into the minor Palm-Graham framework gives it a level of respectability, scientifically speaking, that I don't really think it deserves. All right, let's move on to look at some of those examples which don't fit. So take a Portland cement concrete pavement. We know that if we were to plot a fatigue line, like it would look something like that. So there is low strain levels if you can get, in principle, infinite number of cycles. Well, that won't fit the power law relationship. Look at asphalt rutting. Here's some data from a variety of mixes. Now, which of those could fit into this? If you take logarithms, will you get a straight line? Well, you might for one of the curves in the bottom figure, but I think for all the others, you certainly won't. So they don't follow a power law relationship either. What about asphalt fatigue? I said it's got some similarities with a fatigue relationship. Well, here's some 3 asphalt mixes, a foam mix, an emulsion mix, and a dense bituminous mechanical, something like a asphalt concrete. And this data from various people, but plotted on this chart. So let's fit this to the, it's not exactly the fourth power law because we're using a strain relationship ratio here, not a load ratio, but forgive me for a moment. So the slope of this line, if you convert that to F, it will give you 4.35. Well, that's close to 4, isn't it? Sounds good. What about this one? Well, that's going to be 2.56, or the final one, that's going to be 2.4. They're quite a long way from 4, aren't they? Here's some other data, various mixes. F, if you use it that way, somewhere between 2.5 and 3, not 4. But when we do a strain control test, and most fatigue testing on asphalts is strain controlled, we're actually getting a reduction in stiffness with loading because we're getting damage as we go along. So actually the stiffness is dropping. So therefore, to produce the same strain, we don't need as much load. So they're not constant loading tests as pavements were in the Azure road test. So here's some data from which you'll see how the modulus is effectively reducing. Well, the stress is reducing, but because the modulus is reducing, just in order to keep the strain constant. There are a few published data for stress fatigue lines. Here's one, which I dug out from somewhere. So you've got stress vertically rather than strain. we can draw a straight line through it. So it looks again like a fatigue line, but notice this is not a logarithm of tensile stress. It's a natural scale. So if we're going to plot that with a power law, we'll need to use this equation, and F, if that equation, would be 1.2. So doesn't seem to work with stress either. What about granular materials, which I know more about? Well, I work with Sabina Leisner, she's now in Dresden in Germany, and she's done lots of testing on aggregates, and you can get different types of behavior at different load levels. A low range level, things stop, the rutting stops. Range B, it goes, and then eventually will begin to accelerate. Range C accelerates very quickly. You won't model any of those with a power law. Here's a pavement we constructed quite a long time ago now in Scotland, showing the rutting. And in this one, we put over vehicles of different, axles of different weights. So in phase 1, we've got a vehicle with a front axle of 3 tons of width and a rear axle of 8 tons. And if you use the fourth power law, that equivalence is to 1.01 standard axles. And we did 1,000 passes of that vehicle, which is nearly 1,010 standard axle passes. Then we did some additional load for 115 passes, and then a really very high load for the remaining 1,000. So again, using the fourth power law, you can see that the equivalent number of standard axles goes from 1.5 to 6.3 on each vehicle. Okay, so let's look at the data for that. Here's a typical bit of data. So in this section, when we've got about 1 standard axle going over it, you'll see that initially there's some rutting, and then it more or less stabilizes. On another section, it doesn't stabilize, but goes up fairly linearly. Remember, we're changing at 1,000 passes. So you can see how it increases suddenly at 1,000 passes. I'm sorry, the dotted line is not in the right place, is it? The dotted line has shifted. Dotted line should be a little next to the previous square. Beg your pardon for that. But you can see how the green line suddenly, when we put the extra load on, shoots up very much quicker. The red line, which had stabilized, then goes into a steady increase. So here the rutting stops. Here this rapidly fails. Here the rutting restarts when we put the loading on, extra loading on, but it's still going up in an orderly fashion. So we've got different relationships for different loading and different materials. The power law doesn't work because deformation can stop at low stress levels. It can stop and then restart when we increase the load a bit, and we can get this runaway rutting as well. Rut development wasn't linear or logarithmic with N. And if you did try and push a power law to relate the before and after the low load and the heavy load axles, depending on the pavement, we could get somewhere between F equals 1 and F equals 20. Here's a thicker pavement. This was some work done a long time ago in Australia. Here is using the accelerated loading facility, the ALF machine. So you'll see that they've got 2 loads, an 80 kilonewton, 8-ton axle, and 120 kilonewton load. So the ratio, 1.5 times bigger, the second loading. Now, this distance between these is about 4 times. So that would suggest a power law of 3.4. 1.4 at 5 raised to the power 3.4 gives you 4, which is the distance, the difference. So there seems to be a 3.4th power law. Maybe that's not too far from 4. What do you think? But had we done it down here, look at the difference here. The difference here is only a factor of about 2.5. So certainly we get a much lower power law down there. Certainly doesn't work down there. Some other Australian data. Here, sorry, they've got the subgrade strain this is looking at, which is, we often relate that to rutting of a pavement with equivalent standard axles using the fourth power law along the bottom. So there's some relationship for a range of pavements. I think it was about 25 pavements, very relatively thin asphalt. And they looked at the vertical transient subgrade strain in the pavement. They had instrumented pavements. So they related that to rutting failure, and they found that they could say the number of equivalent standard axles was related, this relationship here, to the vertical subgrade strain EV raised to the power 7.4. So maybe this is a 7.4th power law, but it's really a consequence of the analysis, because the non-standard axle loads which weren't actually at a standard axle were equivalents to a standard axle in order to do the working. So they've made a fourth power law assumption at the beginning, and then they've done a linear elastic analysis to help them with their interpretation as well. So the result is rather a little bit of an artifact, but it doesn't look like F equals 4. Here's some lessons from the heavy vehicle simulator, which was used in Scandinavia. They had two loads, 50 and 70 kilonewton wheel loads. And they trafficked pavements with a 50mm thick asphalt. So quite a thin asphalt. Here's the data. So you can see that they put over, I don't know, was that 70,000 passes, something like that. And you see the rut depths developing with the two axle loads. They did a shift at the beginning because of some initial settlement. So we need to replot that like that. And now if we take, say, for example, a critical rut depth of 10mm, then we're going to get the number of passes at the low axle load to achieve 10mm and the number of passes at the high axle load to achieve 10mm. And we can take those two values of n, make a ratio of them, and we can plot that on the left of this figure. So on the left of this figure, you've got that ratio M1 over N2. And that has been plotted in this figure against the depth of rut. So at the 10mm one, which I just indicated, you can see that the ratio of the number of passes is about 12. But as we choose other rut depths, we get other ratios of M1 and N2. It's not a constant ratio with the different rut depths. So if we interpret that in terms of a power law relationship, because we know what P2 over P1 is, that's a constant, 70 over 50, then we're going to get power laws somewhere between about 4 and 9. 4 occurs at a rut depth of, sorry, my blue arrow shifted there, a rut that occurs at a rut depth of about 2.5mm. So you can see that that's probably an unrealistic rut depth to design a road to. You might want to design it to 10mm or 12mm rut depth, in which case you need a power law of 7 and a bit, 8, something like that on this trial. Some more data, this time from New Zealand. They have a rotating accelerated pavement testing machine, and they tested some pavements with two loads of 40 and 50 kilonewtons. Again, they had thin asphalt, and here's not actually one of their pavements, but similar to one of their pavements. And here's the data they obtained. So it's not actually rutting which is being plotted here, it's something similar, which I'm not going to explain. Vertical surface deflection, but it's akin to rutting. So here you've got the 40 and 50 kilonewton tracks for pavement D, whatever pavement D was, and then you've got the 40 and 50 kilonewton tracks for pavement B and other materials, different construction. So there was large initial deformation in these, up to about 20,000 passes. After that, there was, broadly speaking, a linear progression of decay. They tried to model this using a power law, and they required F value somewhere between 3 and 9, not 4. So they thought maybe we should model this in two parts. An initial deformation, this compaction, this what happens in the first 20,000 cycles, and then this more or less linear bit afterwards, what they call wear. So in this case, they took this bit down here as the compaction bit, and then they took this bit here as the wear bit. and they tried to fit a power law relationship to both of those. And here's their data. So you can see for the compaction element, they got values between about for F, between 0.8 and 3.4, not 4. And for the wear element, values around 1 up to about 3. Again, not 4. Always less than 4 in this case. There's a large variation though, depending on the particular pavement construction. I could show you some more data from South Africa, performed in 1984, again using heavy vehicle simulator trials. They got F varying between 1 and 13. The granular pavements, 1 to about 8.5. They found you got higher values if the aggregate was crushed and dry, lower if it was wet or uncrushed. Chen and others did some work in the at Krell, and they found that for F was with a range of loads, they found that F was greater than about 8 for most of the trials, and that increased with water content or granular bases, because some of there was asphalt bases. All right. So what I've tried to show you here is that if you look at data which is available, you can get almost any result out of it. So let's have a little bit of discussion about this before I wrap up. We've seen that underwriting it, unintentionally perhaps, but underwriting the fourth power law and its use, its application, is the assumption of a fatigue relationship. But fatigue, fundamental to fatigue is that you consume fatigue life. As you do cycles of loading, you consume some of the life. So the damage has got to build with the number of passes. But we've seen that for several materials, concrete, asphalt, granular materials, there can be quite a number of cases where actually damage doesn't build with number of passes. Stresses are low, and it doesn't build with number of passes. And we might imagine in thick pavements, the strains and stresses at the bottom of the pavement are not going to be very large, and therefore at the bottom of the pavement, we may be not getting damage at all. So that's the first problem that we've got with it. I think we've seen that little of the approach derived in the original Azure road trial is really appropriate for what we do with pavements today. As I said, explained to you already, the Azure road trial was based on consecutive passages of the same vehicles over one road. And it was assessed by serviceability, not by the structural things that we're generally interested in modern pavement design. We're interested in fatigue or cracking or maybe other failure modes, shoving or whatever. And we try and have sophisticated models to look at those. But we don't relate it to serviceability, to a panel of riders. So rather different. But equivalency and cumulative damage are nevertheless really attractive. I might also say seductive ideas, because they allow us to simplify things for our pavement design. And simplification is something we like, obviously, because that makes our life easy. But we've got a very complex thing. And if we don't simplify it, what are we going to do? We can't possibly design pavements for every individual loading, at least not at the moment. I think I've shown that some of the data suggests that rut development could be modeled as a hyperbolic, in other words, it increases at the beginning and then stabilizes, or as a two-stage compaction, then wear. Some, not all, by any means. So maybe we should look at our decay models differently and have phases of decay and not assume one type of decay is operating all the time. In the ones I showed you, that wear element might be linear, and at low loads, or maybe log linear at higher loads. It's clearly really important to assess whether there could be stabilizing response. If you think that your pavement is going to stabilize, the limiting stress or the limiting strain values for a stabilizing response have got to be determined somehow. And that's got to be our target, because if that's the case, we can design for that strain and that stress. And we don't really care how many cycles it takes to get there if it's going to stabilize. If there's going to be steady damage, maybe we can use a power law approach, even if it's scientifically spurious. It may work some of the time, but it's clearly got very limited applicability if we do that. And if there's runaway failure, we need to know what that limiting stress for steady damage is so that we don't exceed that. So we need to know the bounds of that area in which steady damage takes place. I think I've shown you that materials don't follow a power law approach. So we really shouldn't expect the pavement to do so, as the pavement is just a combination of a series of materials. It would be really surprising if a power law applied to the pavement when it doesn't apply to the materials. Sometimes power law models don't work at all. And when it does, F is seldom 4. It's highly variable, even in controlled trials, let alone in real pavements where all things are changing. It's very dependent on materials and on the condition of the materials, and it's dependent on the failure criteria we apply. And as I said, it's not usually 4 either. Maybe if initial damage is included, it ought to be 7-ish, maybe, but I mean, it's a very big maybe. If we separate them out, maybe it should be less than 4, maybe, probably even, I don't know. So I asked you a question at the beginning. Do you believe in UFOs? Do you still believe in the 4th power law? If you were agnostic at the beginning, I hope you're now an atheist. Thank you very much.
Thank you, Professor, for that very inspiring presentation. Do we have any questions from the room? Yes, please go ahead.
Okay, very thought-provoking presentation. I appreciated that, and I have to confess to not really having known what the 4th power law was before, but I looked it up before coming here, and they talked about the damage caused by a bicycle. But I think knowing the history of where it came from with the Ashto Road test, I'm sure they weren't riding bicycles around the track. So I think that speaks to your point of you need to know some threshold of where damage might even begin to occur. But my question is, this concept of easels is pretty pervasive. I mean, do we throw it all out, I guess is what I'm saying, or is there a better criteria that could be used in lieu of easels, like right now, that's available?
Yeah, I mean, that's the $1 million question, isn't it, really? Clearly, it's so embedded in pavement design that it would be difficult to throw it out. Even if we find it spurious, even if we doubt its validity, then it's going to take an awful lot to shoehorn people away from it. If you know anything about pavement engineering, you know that the Californian bearing ratio was invented in, I think, the 1930s. And people are still using it, though it has very little relationship to anything. So, we can't get rid of something like that. We can't just demolish easels overnight. What I've tried to show you is, though, that we've got to be wise in the use of it and not take it as the gospel truth. It's got some applicability simply because we don't have anything better. But on the other hand, it's very far from perfect. And sensibly, we ought to know, make an assessment of how far from perfect it is, if not in a quantifiable way, at least in a qualitative way.
A related follow-up, do you have an idea of where in, design or practice, the shortcomings of easels is most likely to, have your outcome differ from your prediction? Where would you most likely see that impact?
Well, for pavements which are thick, or the loading is low, I mean loading in terms of axle loads, I mean here, not number of passes, then we might expect the bulk of the pavement to last forever. Yes, we're going to have to do surface treatments because there's loading going on at the surface, which is not just loading, it's braking, scuffing on corners, all things like that sort of thing. So there are other loads being applied to the pavement, acceleration, braking, so on. So yeah, we're going to need to know about surface defects, and we're going to have to replace those. But at the depth of the pavement, perhaps we'll never have to fix it. And that is some of the idea behind what has been called perpetual pavements. The idea that you design the bottom of the pavement so that it never fails, so you never have to dig it up. All you have to do is do a fashion job on the surface from time to time. So I think that's one area. I think the other area that has got to be is if you've got weak pavements, because weak pavements are going to fail, not because of the fourth power law type of loading, but because they're overloaded. And I think therefore we've got to know where those bounds are.
So I have a realization during your answer that, yeah, where it's most valid is where your typical load is as close to the easel value as possible. And then obviously, like the case of a bicycle, you don't get any damage, and an extreme overload, you can't account for that with any number of easels because the damage happened right then. So yeah, thank you for that clarification.
Yeah, that's right. Yeah.